Sorry, instead we have to open on desktop. Yes, is the PowerPoint visible to you?
Yes, sir. It is visible, sir.
Yeah, fine. So we can start. So today we are going to look at the 5 heat and mass transfer. So in this we have the syllabus like modes of heat transfer, then heat conduction in parallel, radial and composite walls. So it's purely heat conduction. Then we have a heat conduction through hollow, composite cylinder and spheres. Then we have to know the basic convective heat transfer. Then we have to know the fundamentals of radiative heat transfer. Then then the second part is flow through heat exchangers. Then in that, so we have to found the LMTD, that is logarithmic mean temperature difference for parallel flow, and AMTD, that is arithmetic mean temperature difference for counter flow heat exchangers. So we will look at one by one. So first we have to know the modes of heat transfer. Then what is heat transfer first? Then what is mass transfer? Then the different modes of heat transfer. Then what is heat exchanger? Then the types of heat exchanger. Then the temperature differences in the heat exchangers. Then first we can enter into the chapter. What is heat transfer? So actually heat is a form of energy that can be transferred from one system to another as a result of temperature difference, right? So the heat transfer can be identified by the difference of temperatures. The science that deals with the determinations of rates of such energy transfer is heat transfer, right? So there is a temperature difference, right? So it will happen because only there is energy transfer. So that can be called as an heat transfer. So in practice, we are more concerned about the rate of heat transfer. So we know very well about the heat transfer and the amount of heat transfer. So we know only the heat transfers, the rate of heat transfer. So this much amount can be transferred, but how much amount the heat is transferred, we can't identify. So like the heat treatment of metal, so like annealing and quenching, we can able to only identify the rate of heat transfer instead the amount of heat transfer. Then we can look the real-time applications of heat and mass transfers. So to understand the philosophy through experience, so we have some real-time heat transfers. So you may know this part in the bare Pentium 4 processor. You were aware. So you might seen this Pentium 4 processors in your computer or your laptops. So actually this is provided in your laptops for the function of heat transfer. Then this heat things for Pentium 4 also is provided in your systems or in your lab for the purpose of heat transfer. So if you see the hardware of your computers, then you may identify this part. Actually this is a heat sinks. Then this Pentium 4 while performing will be look like this. So there will be a flow fan. So this sink will absorb the heat, and through this fan, we may transfer the heat from the system to the surrounding. Then the heat transfers, actually this is an engineering science. You know what is heat transfer, and you know what are the laws of heat transfer. According to the first law of thermodynamics, the first law is establishes a relation between heat and work, that you know very well, that is energy interaction. And in the second law of thermodynamics, Any questions, ma? Students, am I audible?
Yes, sir.
Okay, so there is some interaction, distractions. Right. So you know very well the first law of thermodynamics establishes a relationship between the heat and work. Then the second law of thermodynamics state that the spontaneous energy interactions are unidirectional. So the second law will state the directions of the flow of temperature. Then the thermodynamics is totally silent on the question the rate at which the heat transfers, right? So we studied a lot about the about this thermodynamics of the systems, but the thermodynamics won't tell about the rate at which the heat travels. So also how to control the rate of heat transfer. Then the heat transfers is an engineering science to design thermal infrastructure. So actually we have to know the thermodynamics as well as the heat transfers to get a good design about the thermal infrastructure. So this it evolved over 200 years. So actually this heat transfer is evolved around 200 years. So there will be evaluation day by day. So the applications of mass transfers were stated here. So the mass transfer, the transfer of mass into or out of the substance can be identified as a mass transfer. Then the transfer of a chemical compound from one phase to another phase is can be called as mass transfer. So examples are evaporation. So you know evaporation process. So in evaporation process, the liquid will converted into gas. So during this evaporation process, there will be a mass difference, right? So you identify the mass difference during this evaporation process. So you may just wait the amount of mass of the liquid. After the evaporation process, you may identify the mass of the gas. So if you measure both, we can definitely able to found the difference in the mass. So this process is called as a mass transfer. Also, we have another example of a mass transfer in diffusion. So you know what is the diffusion process? So diffusion process will in this diffusion process there is a concentration difference. So high concentration may change into low concentration after the diffusion process. So in this diffusion process also we may found the mass differences. So that is called as a mass transfer. Then we have the various mass transfer phenomena here. So one is evaporation. So these evaporation can be happen in processes like drying, then concentration, then baking, then frying, then boiling. So during these processes, this evaporation process will happen. That is from liquid to gaseous form will happen. So definitely there will be a mass transfer. There is a mass difference, so we can found that mass difference is happening because of the mass transferred. Then another example, diffusion. That so these are the real-time applications of diffusion processes. So salt through cheese curd, then smoke through meat, then marinate or curing solution through meat, then line tomato peeling are the real-time applications of diffusion process. So in this diffusion process, like high concentration will be converted into low concentrations. So transfer. Right. So actually, so you may get confused about the moving of fluid from one place to another is mass transfer. That is not actually true. Actually, this moving of fluid from one place to another is not considered as mass transfer. So for a particular amount, so during the phase change will happen, right? So during the phase change, the mass transfer is actually the mass transfer. So just don't get confused. The moving of fluid from one place to another is mass transfer. So it's actually not true. The exact statement about the mass transfer is for a particular amount of substance. The mass difference during the phase change is called as a mass transfer. Then you know the process osmosis. During your school days, you may know this process, osmosis. Osmosis is the net movement of water across a partially permeable membrane from a region of high solvent potential to an area of low solvent potential up a solute concentration gradient. So the concentration gradient will happen in this osmosis process. So osmosis is responsible for ability to plant roots to suck up water from the soil. So each and every plants, this osmosis process will happen in the roots to suck up the water, and this will send to the roots, to the stems. Then since there are many fine roots, they have a large surface area, right? So we need more surface area to get this osmosis very effectively, because water enters the roots by osmosis and generates the pressure required for the water to travel up to the plants. So this osmosis process will generate more pressure. Then only this the water sucked by the roots will travel to the stems. Then osmosis can also be seen very effectively when potato slices are added to a high concentration of salt solution. Just you can do the demonstration in your home. So just you have to take a potato slice and you have to add that potato slice to the high concentration salt solutions. So what will happen? So the water from inside the potato moves to the salt solution. Then this will cause the potato to shrink and to lose its turgor pressure, right? So because of loss in turgor pressure of potato, so this will try to sink. Then the more concentrated the salt solution, the bigger the difference in size and weight of the potato slice. So you can check with the different concentrations of salt solutions, then you may identify the these points. So the more concentrated salt solution will bigger in difference in the size and weight of the potato slice. So actually this is the real-time applications of the mass transfers. So then for example, we can take another example also. Okay, you can take the fresh water and the salt water aquarium fish placed in water of a different salinity, then that they are adapted to will die quickly. Yes, we can conduct this experiment also, and in the case the saltwater fish rather dramatically with the another normal water fish. Then another example is the diffusion of oxygen and carbon dioxide across the alveolar capillary membrane. That will happen in your lungs. So actually in your lungs, so there will be a diffusion process will happen. So the oxygen and the carbon dioxide will diffuse from the inhaling air to the blood is happening because of this diffusion process. So all gas movement in lungs occurs as a result of positive diffusion, like gas moves from one region to another only when the partial pressure of gas is greater in one region to the another region. So actually our inhaling air pressure is high. Then this because of the diffusion, this oxygen and carbon dioxide will transfer to the bloods. So the transfer of gas from the always to the blood occurs by simple diffusion process, right? So actually this is the example of diffusion process, that is mass transfer. The rate of transfer depends on what we have the questions here. So to clarify that, we have to look more about the heat and mass transfers. Also we have the another example of desert cooler. So we know the parts in desert coolers. We have evaporator intake air. Then after some processes, we will exhaust the air duct. Then in the component of desert cooler, we have condensate tank. Then we have a condenser in intake air filter. Then we have a cooling duct. Then cooling air is passed through this cooling duct. Also, we need to get a filter to clean the air. So the condenser, the purpose of the condenser. So this condenser actually cools the air in the desert cooler. Then the cooled air is passed to the space where we want to cool. Right. So actually, the high temperature air is cooled with the use of condenser. Actually, there will be a temperature difference. So this temperature difference is called as a heat transfer. Then we know the evaporative cooling. The cooling through the evaporations of water is an ancient and effective method of lowering temperature. The examples, both plants and animals use these methods to lower their temperatures actually. So there is a term evaporative cooling, so that will happen in both plants and animals in on our real-time applications. So actually, the trees through the process of evaporation, for example, remain cooler than their environment. Then the people accomplish the same thing when they prescribe. Then for both the trees and people, the underlying scientific principle is same. That is, when water evaporates, that is changes from a liquid to gas, it takes heat energy from surrounding to environment. So what will happen if the water gets evaporates? It will take heat energy from surrounding to the environment. So thus leaving its environment cooler. So this is the principle behind the trees and also uh, the people. The people to get cooling these environments. So there is another primitive products available. So finally, some of us may have discovered that water kept in a canvas bag, then porous glaze container, or in a canteen with a water soaked cloth cover is much cooler. Right. So these three examples is much cooler because, especially on a hot day, then water kept in a plain metal or plastic container. Just you can differentiate these two. So actually, if you keep your water in a plain metal or a plastic container, is hotter compared with these kinds of primitive products like a canvas bag, then porous clay container like mud parts, then or in a canteen with a water soaked cloth cover. So this will actually be a cooler one. Why it happens? Because as the water evaporates from surfaces of this container, it draws heat away from the containers and the water they hold, as well as from the air around them, thus leaving water cooler. Right. So actually, the evaporation process happening in the surface of these containers will transfer heat. So then we can get the cooling of the water. So actually, this is the principle behind these primitive products. Then there is three mechanisms of heat transfers. So there is we have conduction, we have convection, and we have radiation. These are the modes of heat transfer. So for your easy understanding, so this figure will show you the processes of conduction, convection, and radiation. Just you may follow the three paths. So like there is a water, and in B we have a fire, right? So how can we try to control this fire? So we have three chances. We have three possible ways. So one is we can take water and transfer it to person by person. Then finally we can use this water to control the fire. So there is one possibility, and another second possibility is, so first possibility is through this fire extinguisher we can pump the water to the to control the fire, and second is we can pass the water to control the fire. Then we can directly flow from water source to control the fire. So there is three possibility way. So this first path will actually is a radiation process. So from directly. Then the second process is like conduction. Then the third process is like convection. So we may get more clarification about these modes of heat transfer by looking the next previous slides. Next slides. So there are mechanisms of there are three mechanisms of heat transfers. So heat can be transferred in three different ways, like conduction, convection, and radiation. So all modes of heat transfers require the existence of temperature difference, right? So the principle behind this is temperature difference, and all modes of heat transfers are from the high temperature medium to low temperature medium. Actually, we know the second law will state there is a heat transfer from high temperature to low temperature. So these modes of heat transfer also will follow that. Then these are some examples of the heat transfer. So for example, take this first example. So to heat this water in a container, we may we may we may feel these three modes of heat transfers. So the conduction process. So if water gets heated, then this if assume this handle is made up of steel. So what will happen after sometimes the heat will transferred through this uh, handle, and your hand will feel the hotness of the handle, right? So this process is because of the conduction. Then the temperature inside the liquid, inside the water, is increased. You may identify the increase in temperature in the liquid is because of the convection. Then the radiation is the heat of this heat source is directly uh, field fiber hand is called a radiation, right? So there is a three possibility of heat transfer. So we have convection and we have radiation. Then another example is a, a cup containing a hot coffee. So for example, if coffee is around 70 degrees Celsius, then definitely there is a there will be a heat transfer, and to the environment, that will the temperature is 20 degrees Celsius, right? So the surrounding environment is 20 and the system is 70 degrees Celsius. So according to the second law, definitely there will be a uh, heat transfer will happen. ஃபைன் கண்ணா கேக்குதாம்மா? ஜெயராமன்
சார் கேக்குது சார்.
எப்பமா கட் ஆச்சு? எங்க சிஸ்டம் ரீஸ்டார்ட் ஆயிடுச்சுமா ஆட்டோமேட்டிக்கா.
இப்பதான் சார் ஒரு 2 மினிட்ஸ்க்கு முன்னாடி.
எந்த ஸ்லைட் பார்த்துட்டு இருந்தோம்? மோட்ஸ் ஆஃப் ஹீட் ட்ரான்ஸ்ஃபர் பார்த்தோம் இல்லையா?
சார்
இது வந்து இல்லையா?
ஸ்லைட் தெரியல சார் உங்களுக்கு.
சரி ஓகே, ஸோ யூ கேன் ரெஸ்யூம்.
விசிபிள் ஆகல சார் ஸ்லைடு.
வெயிட் ஐ வில் ஷேர். இப்போ தெரியுதாம்மா?
சார் தெரியுது சார்.
So I think we have disconnected in this slide, so we can continue from this. So we may identify these three modes of heat transfer during the process of heating water. So heat conduction will happen in the in this solid, then this heat convection will happen in this liquid, and this heat conduction radiation will happen in this gaseous region. Then in this example, so actually the hot coffee is having a 70 degrees Celsius and the environment is around 20 degrees Celsius, but definitely there will be a heat transfer. So the possibilities are may happen. So from this through this surface of this container, the conduction will happen. So this conduction will happen through this surface of the container to the environment. Also there is a possibility to the radiation, the convection from the liquid to gas, so liquid to the environment. Then you may take this example. So a thermos bottle, so there is no heat transfer will happen because insulated. Then you may take this another example. So cold drinks or heat flow in the direction of decreasing temperature. Actually this is the example of heat flow in the direction of decreasing temperature. So in our atmospheric temperature is take an example 20 degrees Celsius. The cool drinks will have only below this temperature. So there will be a heat flow from this surrounding to the cool drinks inside the tin. So these are some examples of heat transfers. Then we have three modes of heat transfer, that is conduction, convection and radiation. Then we may define the each and every process. Conduction refers to the transfer of energy in a medium due to temperature gradients. Then in contrast, the convection refers to the heat transfer occurs between the surface and fluid at rest or in motion. So when they are at a different temperatures. So yes, we can take the conduction will be happen in a medium due to the temperature gradient, and the convection will happen between the surface and a fluid. That may be because of the molecules in the rest or in the motion. Then the third category is thermal radiation. So this will refers to the heat transfer that occurs between two surfaces at different temperatures. That is, it results from energy emitted by by any surface in the form of electromagnetic waves. Actually, this radiation will happen because of the electromagnetic waves. Right. So just from this example, we may get a clarification about the conduction, convection, and radiation. So this the heat transfer from this heat source to the hand is because of through this solid medium is happening because of the conduction. Then you may feel the temperature above the heat source is because of the convection. So actually there is a air inside this region. Then through the electromagnetic waves, the heat is transferred to the hand, that is called a radiation. So actually this so conduction will happen in the solids. So we may feel the conduction of the heat in the roads to the body of your legs. Then physical mechanisms of conduction. Then the temperature is a measure of kinetic energy of the molecules. Right. So in the conduction, the temperature is a measure of kinetic energy that you know very well. In a liquid or gases, the kinetic energy of the molecules is due to the random motion of the molecule as well as the vibrational and rotational motions that you know very well. When two molecules processing different kinetic energies collide, part of the kinetic energy of the more energetic molecule is transferred to the less energetic. Actually, this kinetic energy is transferred from the more energetic molecules to the less energetic molecules, particles. In solid, heat conduction is due to two effects. One is the lattice vibrational waves. So these lattice vibrational waves induced by the vibrational motions of the molecules positioned at a relatively fixed position in a periodic manner called a lattice, and the energy transferred via free flow of electrons in the solids. So there is a two possibility of the heat conduction in solids. One is lattice and is another one is through lattice, and another one is through flow of electrons, that is because of electronic components. Then in thermal conductivity of a solid is obtained by adding the lattice and the electronic components. The thermal conductivity of pure metal is primarily due to electronic components like the electrons, flow of electrons. Then whereas the thermal conductivity of non-metals, so in metals the heat transfer, heat conduction is purely because of the electrons. Then for non-metals, the conduction, heat conduction will happen because of the lattice components. Actually, lattice is a vibrational waves induced by the vibrational motion of the molecules. Right, so vibrational motions of the molecules will happen to transfer the heat in the lattice, and the electronics, the flow of electrons also will conduct the thermal energy in the pure metals. Then you may identify these the lattice components of a thermal conductivity strongly depend on the way the molecules are arranged. So you know the structures of the molecules. For example, the thermal conductivity of a diamond, which is highly oriented crystalline solid. So you know uh, uh, crystalline material, then non-crystalline material, then partially crystalline materials. So depending on the crystallinity of the material, the thermal conductivity will vary. So actually this diamond is having high crystallinity, so there will be high heat conduction, thermal conduction will be happen. So the thermal conductivities of the another of some pure metals will be stated in the table 1.1, that will be in the next slides. So actually this will happen. Right, so there will be a vibration. So if if one end of the rod is heated, so there will be lots of vibration in the heating end. Then this vibration is transferred through this portion to get transfer, that is called conduction. So heat travels along the rod will in this direction. Then if the heat is compared in the another end, so there will be not much vibration. So we can differentiate the rods as hot end and cold end. So based on the vibrations of the molecules. So if the solid gets heated, the lattice will get vibration. Then these vibration motions will transfer to get the heat conduction. Then there is another example for conduction. Conduction is the transfer of energy from more energetic particles of the substances to the adjacent less energetic ones as a result of interaction between the particles, that you know very well. Then conduction can take place in solids, liquids and gases. So don't take only conduction will happen in solids. So in all the three modes the conduction will happen. On this three phases the conduction will happen. In gaseous and liquid, conduction is due to the collisions of molecules during their random motion. So in liquids like uh, all the liquids, the conduction is due to collision of the molecules during their random motion. Then in solids, it's due to the combinations of vibrations of molecules in a lattice and the energy transport by the free electrons. That you know very well. There is a two possibility of conduction. One is because of the lattice and another one is because of the transfer of electrons, that is free electrons. Then in this example, a cold canned drink in a warm room eventually warms up to the room temperature as a result of heat transfer from the room to the drink can by conduction. So actually this aluminum can will conduct heat from the environment to the system. So actually this cola canned in a cold drink will have low temperature compared with the surrounding temperature. So the high temperature will transfer to the cold one. So through this aluminum can. So this wall of aluminum can will transfer. So we have to consider the thickness of the aluminum can. Also, so the temperature outside the surrounding will be high and the inside system will be low. So there is a temperature difference. So this temperature difference will causes the heat transfer. Then the formula of heat conduction. So the conduction, it is observed that the ratio of heat conduction through the layer of a constant thickness is proportional to the temperature difference across the layer and the area normal to the directions of heat transfer and is inversely proportional to the thickness of the layer. So this heat transfer can be calculated with this equation. So that is q dot through conduction will be equal to kT into A into delta T by delta X. So here delta T is change in temperature difference and this delta X is thickness, constant thickness, right? So then we have the area that is normal to the flow direction. Normal to the flow direction. Actually, this is the area normal to the flow direction. Then this KT is actually a constant. This thermal conductivity. KT is constant of proportionality. KT is thermal conductivity of a material. So each and every material will have its own thermal conductivity. So this is actually given in your table. in the next slides. Why? Add a network quality. Recording dismiss. Right, connect ஆயிடுச்சாமா? Students, connect ஆயிடுச்சாமா? Connect ஆயிடுச்சா?
Yes, sir. Yes, sir.
Yes, sir.
Fine. So this is the equation for calculating the conduction in heat transfer in conduction. So heat Q dot will be equal to KT into A into delta T by delta X. So here KT will stands thermal conductivity of material what we used. Then A stands the area of the solids normal to the heat flow, heat transfer. Then the delta T stands the temperature difference, and delta X, you know, the thickness of the solid. Then each and every material has its own thermal conductivity. So like copper and silver are good conductors, good electrical conductor. So this electrical good electrical conductors also will conduct heat more. So therefore have high thermal conductivity constants, KT values. Then materials such as rubbers, woods, and triforms are poor conductors that we know very well, like in both electrical conductivity and thermal conductivity. So these materials will have low KT values. So actually so this will show you the thermal conductivity of the materials at room conditions. So you may get the values of KT from this table. So the diamond actually has a high KT value compared with all other materials. So silver has 429 watts per meter Kelvin. Then so the unit of the thermal conductivity is watts per meter Kelvin. So the diamond has a higher thermal conductivity KT value than the urethanes. Then rigid foams has a lower KT values. So we can take the rubber, soft rubbers as 0.13 watts per meter Kelvin KT value. So we can take these values to calculate the thermal heat transfer of the in the conduction process, right? So the heat transfer depends on the thermal conductivity of the material. So because the heat transfer is directly proportional to the thermal conductivity of the material. So in this example, the copper has the KT value around 401 watts per meter meter Kelvin or degree Celsius, and this silicon has the KT value around 148 watts per meter Kelvin. Then there will be a we can take the differentiate between these two material. Actually the transfer of heat is same, right? So the thickness will be same 1 meter of silicon and copper. Then the temperature difference is also same, means we can get the difference in the heat transfer. So if you use copper, we can get more heat transfer compared with the silicone material. So if we want to choose a suitable material for the heat transfer, we have to know the have to choose the suitable material with the suitable KT values, that is thermal conductivity values. So each and every material will have its own thermal conductivity values. So depending on our requirements, we have to choose the materials. Then these are the range of thermal conductivity of various materials at room temperatures. So just we can compare that. So hydrogen and helium, then air, carbon dioxide will be in this range from 0.01 to 0.1. So this will have less heat transfer. Then we have actually this in these mediums also. Actually, these are gases, right? So these are gases, but in this medium also the conduction will happen, right? So in liquids also the conduction will happen. In solids like metals and then pure metals, metal alloys, and non-metallic solids. In solids also the conduction will happen. But in solids, there will be more conduction, heat transfer through conduction will happen because the KT value of this solids is more compared with the liquids and gases. Right. So diamond graphite has more KT values. Then this material can be used to get more heat transfer uh, through conduction. Then we have to know the Fourier's law of heat conduction. So that is actually the another form of the equation of heat conduction. So actually in the limiting case of delta x, that will be if the delta x is equal to 0, then we can get the equation as q dot will be equal to minus kt. So here the term minus will be there. So minus kt A into dx by dt. So this equation is called as Fourier's law of heat conduction, right? So yes, you may assume this hot wall. So this is hot wall. Then this is cold wall. Then this heat transfer will happen through this wall. So assume this x is the thickness of the wall. Then the hot wall will have more temperature and the cold wall will have the less temperature. So according to the thermodynamics law, the heat will try to transfer from high medium to high temperature to the lower temperature. Then this temperature profile will be based on the thickness of the wall. So it indicates that the rate of heat conduction in a direction is proportional to the temperature gradient in that direction. So dx will be directly proportional to dt. Heat is conducted in the directions of decreasing temperatures and the temperature gradient becomes negative. Then when temperature decreases with increasing dx. So actually dx will be equal to dt. So if there is a negative temperature, decreasing temperature, like in the example in the cold drinks, Yes, cool drinks is heat is transferred from the surrounding to the cold drinks will be a temperature decreasing process, right? So definitely we can get the increasing x. So therefore a negative sign is added in the equation to make a heat transfer in the positive x direction, a positive direction, a positive quantity. So just just have this equation as a Fourier law of heat conduction with a symbol minus. Then so this is a problem with the heat conduction. So the cost of, we have to calculate the cost of heat loss through a roof. So just read out the problem. And the roof of an electrically heated home is 6 meter long, 8 meter wide and 0.25 meter thick, and is made of a flat layer of a concrete whose thermal conductivity is 0.8 watts per meter Kelvin or degree Celsius. The temperatures of the inner and outer surfaces of the roof uh, one night are measured to be 25 degrees Celsius and 0 degrees Celsius respectively. So T1 values and T2 values were given. Also KT values also given. Also to found the A, that is area of the normal to the heat flow, they gave the dimensions like length, breadth and width. Then, so for a period of 10 hours we have to determine, so also they gave the time, so we have to determine the rate of heat loss through the roof that night. We have to found the heat loss. Then we have to found the heat the cost of heat loss to the home owner if the cost of electricity is $0.2 per kilowatt hour. Just they gave the T1 value, T2 value, then the area value, then the KT values. Just we have to found the heat loss. So just we can use the formula for heat conduction formula to calculate the first question. So nothing that the heat transfer through the roof is by conduction. So you know, so actually the heat transfer. So actually inside the outside temperature is 0 degrees Celsius and the inside temperature is 25 degrees Celsius. So definitely the heat transfer will happen through the roof. So actually this roof is a solid medium. So definitely there will be a conduction process. So we can take the conduction heat conduction heat transfer equation in the conduction process to calculate the heat transfer. So we can take Q dot conduction equal to KT A into delta T, here is T1 minus T2 divided by X or delta X. So here the X is the length of the concrete, right? So the so we can found the area with the multiplication of that is breadth and width, like 6 meter and 8 meters. Then we can take 0.25 in the wide in the as thickness of the wall. Then we can substitute the values in the equation. Then also they gave the KT value as 0.8, and if you substitute we can get the heat transfer as 3840 watts, that is 3.84 kilowatts. So the first question is solved with the given data. Then we have to solve the second question. So in second question they asked the cost of the heat loss, the home owner cost of the electricity. So that is $0.2 per kilowatt hour. So we can calculate that. So that is calculated by the amount of heat loss through the roof during a 10-hour period. So we have to calculate. We have to account the hours, 10 hours period also, and its cost are determined from the same equation. Q is equal to Q dot delta T. So we can multiply with the time, then we can have the Q in kilowatt hours. Actually they gave the cost in per kilowatt hours, so we have to calculate this kilowatt hour. So the unit of Q dot here is in kilowatt, so we have to multiply with the hours, so actually the 10 hours. So 3.84 kilowatt will become 38.4 kilowatt hours. Then we have to calculate cost per day, means the amount of energy into unit cost of energy. So amount of energy for 10-hour period is 38.4 kilowatt hour into $0.2 will give you the cost per day. that is will approximately $7.68. So if you want to calculate the cost per month, means we have to calculate the cost per day into 30 days per month. Then you will get the cost per month will be $230.4. So you may think why is the bill so high? So because of the thermal conductivity of the concrete, right? So to increase the thermal conductivity, nowadays people were using the epoxy flooring. So the thermal conductivity of these materials will take changes in the thermal conductivity of the other materials, right? So in this way we can calculate the thermal conductivity of the materials in a process. Then the another term is thermal diffusivity. The thermal diffusivity is a measure of how quickly a material can carry heat away from a hot source. Since material does not just transmit heat but must be warmed by it as well, this thermal diffusivity called alpha involves both the conductivity and the volumetric heat capacity rho Cp. So this thermal diffusivity can be calculated with the ratio between the Kt and the volumetric heat capacity, that is heat capacity Cp, rho Cp. That is actually heat conducted by heat stored will be the unit will be approximately equal to meter squared by second. So the heat conducted unit will be joule per meter second Kelvin, then meter cube per kg, or kg Kelvin per joule, or approximately equal to meter squared by seconds. So we can have the thermal diffusivity values for different materials from these tables at room temperatures. So we can take alpha values from this. So if you compare, the silver has more thermal diffusivity, then followed by gold, then followed by copper, then aluminium, then iron, then mercury, marble, ice, concrete, brick, etc. Right? So we can take the thermal diffusivity also to get the heat transfer comparison. So actually this is in the conduction, the modes of heat conduction through and conduction process. Then we have as convection. So convection in the liquids. So you may have these examples. So during heating a liquid in a container, the convection will happen in the liquids. Actually the bottom of the bottom molecules in the water will get heated first, then it will go up, then the heat is transferred to the top portion of the liquids. Then this will the cyclic process will happen, then the whole water will get heated, right? So the cold water circulates to the bottom to be reheated. So if you provide heating in the bottom, so there will be a circulation. Then hot water rises to the surface, then the cold water circulates to the bottom, so there will be a cyclic process. Then the heat is transferred through the convection process in the liquids. Actually, the convection is the mode of energy transfer between a solid surface and the adjacent liquid or gas that is in the motion, and it involves the combined effect of conduction and fluid motion. So just you may feel this. So actually we need a container, that is a solid, and we need a liquid, that is a fluid. So the convection is actually the heat transfer from the medium from solid to liquid, right? So that was stated here, that faster the fluid motion, the greater the convection heat transfer. So we need a combination of these two, so the conduction in the solid and the fluid motion required to get the convection process. So the faster the fluid motion, the greater in the convection heat transfer. So the density will be matter here. So the density, so the lesser density will give you the higher fluid motion. Then in the absence of any bulk fluid motion, heat transfer between the solid surface and the adjacent fluid is by pure conduction. So if the density is more in the liquid, so the convection will happen is purely by the conduction in both in the solid as well as in the liquids. The presence of bulk motions of the fluid enhances the heat transfer between the solid surface and the fluid, but it also completes the determinations of heat transfer rates. Right, so consider the cooling of a hot block by blowing of a cool air over its top surface. The energy is first transferred to the air layer adjacent to the surface of a block by conduction. So just we can take the example. So first the conduction process will happen in the solids. So this energy is then carried away from the surface by the convection, that is by the combined effect of conduction within the air and the motion of the air, which removes the heated air near the surface of the surface and replace it by the cooler air. So uh, in this example of a cooling of a hot block by blowing cool air over the top surface, so this both the conduction and convection process will happen. Then we have in convection, we have two types, that is one is a forced convection and free convection or natural convection. So the convection is called a forced convection if the fluid is forced to flow in a tube or over a surface by external means such as fan, pump or a wind. So we have two different types in convection. So if the flow is forced by any mediums, that we can call as a forced convection. So in contrast, the convection is called a free convection or natural convection if the fluid motion is caused by buoyancy forces induced by density differences due to the variations of temperature in the the normal motion will be there in the fluids because of the buoyancy forces induced by the density differences. So due to the density differences, so the liquid having high temperature has uh, less temperature, less density, and more temperature has more density, right? So more temperature has less density and less temperature has more density. So due to this temperature density difference, there will be some buoyancy forces will be induced. So this induced forces will give you the natural convection. So for example, in the absence of fan, heat transfer from the surface of a hot egg will be by natural convection, since any motions of air in this case will due to rise of warmer air near the surface and fall off a cooler. So the hot egg in the surrounding surface is naturally cooled by the natural convection. because of the density difference. So the air surrounded by the hot egg gets less density compared with the foremost air molecules. So this will try to uh, gets circulated in the surrounding. Then the hot egg will be naturally cool with the free convection or natural convection. Then these are some, we can get comparison between the forced and free convection with the use of this diagram. So the cooling of a boiled egg by forced and natural convection may happen. So if you use any external sources to get it cool, that is called a forced convection. So if the cooling is happen with the natural medium, means that is called natural convection. So actually the natural convection will take time, but there is a two possible way to the process convection. Then the Newton's law of cooling. So the rate of heat transfer by convection is determined from the Newton's law of cooling. So the equation is expressed as Q dot will be equal to H into A into delta T. So here H stands convection heat transfer coefficient. So you know, as in the previous case, A is the surface area through which the heat transfer takes place. Then Ts is the surface temperature, and Tf is the bulk fluid temperature away from the surface. Then the convection heat transfer coefficient H is not property of a fluid like our Kt in the previous case. So it is an experimentally determined parameter whose value depends on the all variables that influences convection, such as the surface geometry, then the nature of the fluid motion, then the properties of the fluid, and the bulk fluid velocity. So all the parameters will influence the H value. So we have to calculate the H value first, then we have to calculate the convection heat transfer through the convection process with the use of this Newton's law of cooling. So the typical values of H will be in the unit watt per meter square Kelvin, or in the range of 2 to 25 watts per meter square Kelvin for a free convection of gases. Then 52,000 watts per meter square Kelvin for the free conversion of liquids. Then 22 to 250 watts per meter square Kelvin for the forced convection of gases. Then it will be around 50 to 20,000 watts per meter square Kelvin for the forced convection liquids. Then 2500 to 1 lakh watts per meter square Kelvin for the convection of a boiling and a condensation process. So we can have the range of the H, that is your heat transfer coefficient, convection heat transfer coefficient, to calculate the heat transfer in the process convection. Then so from this figure we can get the classification. So the heat convection is based on the velocity variation of the air. So if the velocity is more, we can get the temperature variation of air. So it's actually the inverse. Actually this will be in inverse proportion. Then we have the another mode of heat transfer is radiation. So just unlike conduction and convection, heat transfer by radiation can occur between two bodies even when they are separated by a medium colder than both of them. So just we can take this example. A person with the temperature 30 degrees Celsius, and a fire with the 900 degrees Celsius, and air with a 5 degrees Celsius. Actually, so the temperature of a fire is 900 degrees Celsius, then the person is 30 degrees Celsius, but the in between there is a air having temperature 5 degrees Celsius, which was less compared with the person temperature. So in this scenario, there will be a mode of heat transfer will happen because of the radiation process. Uh, so radiation is the energy emitted by the matter in the form of electromagnetic waves, as I said earlier, as a result of changes in the electronic configurations of the atoms of molecules of air. Unlike conduction and convection, the transfer of energy by radiation does not require the presence of an intervening medium. So there we no need a medium of molecule. So in fact, energy transfer by radiation is fastest at the speed of lights. Okay, so we can compare the speed of light with the radiation, energy transfer by the radiation in vacuum. So this is exactly how the energy of the sun reaches the earth. So just we can take the heat energy from the sun transferred to the earth is an example of radiation. So in heat transfer studies, we are interested in thermal radiation, so which is the form of radiation emitted by the bodies because of their temperature. So actually each and every bodies will try to emit the temperature. So it differs from other form of electromagnetic radiation such as X-rays, gamma rays, microwaves, radio waves, and television waves that are not related to the temperature. So we have another electromagnetic radiations such as X-rays, gamma rays, microwaves, radio waves. So actually these radiations won't be involved the temperature. Then all the bodies of the temperatures above absolute zero emits thermal. Absolute zero will emit thermal radiation. So actually each and every body will emit thermal radiation, but it should have the absolute zero temperature. Then the radiation is the volumetric phenomena, and all solids, liquids, and gases emits as well as absorb or transmit radiations of varying degrees. However, radiation is usually considered to be a surface phenomenon of solid that are opaque to thermal radiation such as metals, woods, rocks, seals. The radiations emitted by the interior regions of such material can never reach the surface, and the radiations incident on such bodies is usually absorbed within a few microns from the surface. So the maximum rate of radiation that can be emitted from the surface at an absolute temperature is given by Stephen Boltzmann's law as Q dot will be equal to uh, alpha A into T power 4. That is a temperature of surface power 4 in units in watts. So we can use this formula, the Stephen Boltzmann law, to calculate the heat transfer with the use of in the process radiation. So here, as usual, is surface area, and sigma is Stephen Boltzmann constant, that is 5.67 into 10 to the power minus 8 watts per meter square Kelvin power 4. Then the idealized surface that emits radiation at this maximum rate of body. So you may aware about the black body. So and the radiation emitted by a black body is called a black body radiation. So the maximum a material which is trying to emit the maximum emittivity is called a black body. So if the black body is emitted the radiation that can be called as a black body radiation. Then the emissivity can be added. So the radiation emitted by all real surfaces is less than the radiation emitted by the black body as the same temperatures, and is expressed as this q dot will be E into delta into A into Ts power 4. So actually we have to compare the real surfaces with the black body. So actually black body only will have the 100% emissivity compared with the real surfaces. So because of that we have to introduce the emissivity value in the equation. So where eta is the emissivity of the surface, then the property emissivity whose value is in the range 0 to 1 is a measure of how closely a surface approximates a block body for which E is equal to 1, that is eta is equal to 1. Then we can have the emissivity values in the table at 300 Kelvin, that is room temperature. So the aluminum foil have the 0.07 emissivity value. Then the all other materials having this emissivity values. So we can take the equation for heat transfer. Q dot is equal to eta alpha A into Ts power 4 units in watts. So also there is another term, absorptivity alpha, which is a fraction of radiation energy incident on a surface that is absorbed by the surface. Its value will be also in the range 0 to 1. So a black body absorbs the entire radiation incident on it. That is a black body if is a perfect absorber as well as a perfect emitter. So black body has the alpha value 1, also the eta value 1. So in general, both eta and alpha of a surface depend on the temperature and the wavelength of the radiation. So Kirchhoff's law of radiation states that the emissivity and the absorptivity of a surface are equal at the same temperature and wavelength. So each and every material have these both values for a particular temperature and a particular wavelength. So in most practical applications, the dependence of eta and alpha on the temperatures and wavelength is ignored, and the average absorptivity of a surface is taken to be equal to its average emissivity. So we can take alpha will be equal to eta. Then we can have the rate at which the surface absorbs radiation is determined from Q dot absorptivity will be equal to alpha into Q dot that is Q dot what is calculated in the previous equation, that is emitted. Right, so where Q is the relative rate at which the radiation at incident on the surface, and alpha is the absorptivity of the surface. Right, so for opaque material like transparent material, so like what is transparent material and what is opaque material. So opaque material, for opaque material, the portion of incident radiation that is not absorbed by the surface is reflected back. Right, so we need a transparent material to emit full radiation. So Q the surface absorbs radiation will be alpha into Q incident for transparent material, and for opaque material 1 minus alpha into Q incident. Then the absorption and emission of radiation can be compared with these two comparison. So the energy out will be equal to energy in. The emitted energy per incident energy will be emissivity. Right, so we can have the emissivity as energy emitted energy by incident energy. So we can take the radiant energy from surrounding is transmitted to a medium, then around 0.03 E will be reflected in the lump black coated block. Then we can take a silver coated block. So actually this silver coated block is a transparent material. So actually this material has its own reflected value. Then 0.97% G is absorbed by this material, and only 0.10, that is 10% of E, is absorbed by this silver coated block. Then there is a comparison between the block bodies. So we have lump block coated block, then we have a silver coated block. So the temperature rises rapidly in this lump block coated block, then the temperature rises slowly in this silver coated block. The summer clothing white reflects radiant energy better than the black. You may feel the temperature uh, while wearing a black shirt and white shirt in the summer. So these black bodies will absorb the heat then compared with the white cloths. So until equilibrium is reached, white strips on roads are at lower temperature than unpainted asphalts. Then wrap an ice cube in black cloth and another is aluminum foil and place both in the sunshine. What will happen? So this will happen. So the black body will absorb more heat, then the white surfaces will the temperature rises will be happen slowly. Because of that, the black shirts will feel more heat in the summer. Then the temperature difference between the rates of radiation emitted by the surface and the radiations absorbed is the net radiation heat transfer. So if the rate of radiation absorbed is greater than the rate of radiation emission, the surface is said to be gaining energy by the radiation. Otherwise, the surface is said to be losing energy by the radiation. So there is a two possibility. So the surface may gain energy or may lose energy. So in general, the determinations of the net rate of heat transfer by radiation between two surfaces is a complicated matter since it depends on the properties of the surfaces. So their orientations relative to each other and the interactions of the medium between the surfaces with the radiation matters. Then, however, in the special cases of a relatively small surface of emissivity and a surface area at absolute temperature, that is completely enclosed by a much larger surface at absolute temperature, temperature surrounding separated by a gas that does not intervene with the radiation. The net rate of radiation heat transfer between these can be calculated. The equation Q dot radiation will be equal to emissivity eta alpha into A into change in differences, that is surface power 4 minus surrounding power 4. So in these special cases, the emissivity and the surface area of the surrounding do not have any effect on the net radiation heat transfer. So the large enclosure and the small body and the surrounding of the small body is the matter to give the radiation heat transfer through the radiation process. Just take the formulas alone, we can have these problems. So So simultaneous heat transfer mechanisms also will be there. So not all three can exist simultaneously in the medium. Heat transfer is only by conduction in opaque solids, but by conduction and radiation in semi-transparent solids. Thus, solids may involve conduction and radiation, but not convection. However, a solid may involve heat transfer by convection and or radiation on its surfaces exposed to a fluid or other surfaces. For example, the outer surfaces of a cold piece of rock will warm up in the warmer environment as a result of heat gained by the convection and radiation. So convection is by the from the air, and radiation, but the inner parts of the rocks will warm up by the conduction. So there is a simultaneous heat transfer. Both all the three may be possible. Heat transfer modes will be possible in a surface. So in opaque solids, only conduction will happen. So in gas, there is the conduction. There is a possibility of conduction or convection or radiation also there. Then in vacuum, we can get radiation. So here there is another example. So heat transfer is a body conduction and the possibility by radiation in a still fluid, and by a convection and radiation in a flowing fluid. So there is a two possibility. So in absence of radiation, the heat transfer through a fluid is either by conduction or convection, depending on the presence of any bulk fluid motion. So convection can be viewed as a combined conduction and fluid motion, as I said earlier. So thus when we deal with the heat transfer through a fluid, we have either conduction or convection, but not both. Right, so just note down this point. So if a fluid is involved, definitely there may be two possibility, but we have to take any one. So also gases are practically transparent to radiation, except that some gases are known to absorb radiation strongly at certain wavelengths. So liquids, on other hand, are usually strong absorbs of radiation. So we can blindly say, so the conduction will happen in the solid, then the convection will be happen in the liquids, and the radiation will be happen in the gases. So the combined heat transfer coefficient can be calculated by Q equal to H combination of Ts minus T on infinitive. So just assume this one. So there is a person with 29 degrees Celsius, and there is a atmospheric air with the 20 degrees Celsius. So there is a two possibility waves. So the conduction will be happen here. So convection will be convection also will be there in the surrounded atmospheric air, and there is a possibility of radiation also. So just we can with this problem we can conclude this today's class. So consider a person standing in a breezy room at 20 degrees Celsius to determine the total rate of heat transfer from this person's if the exposed surface area and the average outer surface temperature of the person are 1.6 meters square and 29 degrees Celsius. Right, so they gave the area and they gave the outside temperature. And the convection heat transfer coefficient values, alpha values also given. Convection heat transfer, that is H value also given, 6 watts per meter square degree Celsius. Convection can be viewed as a combined conduction and fluid motion. So we have to calculate the convection. So the heat transfer is from the person by convection and radiation. From the above table of emissivity and human skin. So the emissivity, we can take the emissivity from the table, that will be around 0.95 eta. So we can use the values. So H value is given, A value is given, then TS and T value is given. So just we can use the heated convection formula to calculate convection heat transfer in the convection process. So that will be around 86.4 watts. Then we have to calculate the heat transfer by the radiation with the equation of eta alpha as into T. There is a Ts power 4 minus T surface power 4. So just if you use, then we can found the heat transfer by the radiation will be around 81.7 watts. So in this convection process, so we need to add both together. Convection and radiation process will happen. So just we can compare these two. So during this convection, the heat transfer will be 80 more compared with the radiation process. So this we can stop here. So we can look at the heat conduction in parallel, radial and composite valve in the next class. So this is the introduction about the modes of heat transfer. So we have 3 different modes. There is conduction, convection, radiation. So just to try to remember the formulas alone, then we can apply this formula to solve the problems, right? So that is enough. So just if you have any queries, you can wait here, or else you can hang up.
Thank you, sir.
Thank you.
Thank you.
Thank you.
சார்
சொல்லுமா
சார் இப்போ நீங்கள் அசைன்மெண்ட் கொடுத்தீங்களே சார்
எஸ்மா
சார் அதில் இப்போது டயக்ராம் நான் வரைஞ்சதெல்லாம் கொஞ்சம் சரியா இல்லைன்னா இமேஜ் இன்சர்ட் பண்ணிக்கலாமா சார்?
ரைட் பண்ணியிருக்க இல்லையா?
ஆமாம் சார்.
டயக்ராம்ஸ் மட்டும் இன்சர்ட் பண்ணி கேட்குறியா?
ஆமாம் சார்.
சரிம்மா, பரவாயில்ல.
ஓகே சார்.
ஓகே,
தேங்க்யூ.